Have you ever wondered if a robot, despite its impressive strength, can really handle everything you ask of it? Imagine you are designing a new automated process, and you need to ensure your robotic arm can safely and effectively lift a new component. It is not always as simple as just checking a single weight limit. Interpreting robot payload data sheets correctly is absolutely essential for the safe and efficient operation of any robotic system. These sheets provide critical specifications that, when understood properly, prevent overloading the robot, ensure precision, and prolong its operational lifespan. Without accurate interpretation, you risk damaging the robot, its end effector, or even compromising safety in the work environment. The why behind these detailed sheets lies in the complex physics of robot motion and material science. Robot payload capacity is not merely a static weight it can lift. It is a dynamic limit influenced by several factors. Firstly, you will often see a nominal payload or rated payload. This is the maximum mass a robot is designed to handle under specific, ideal operating conditions, often without exceeding certain performance or lifespan guarantees. However, this number assumes the mass is concentrated at a very specific point and moves within defined speeds and accelerations. A critical, yet often overlooked, factor is the center of gravity of the payload. If the payload center of gravity is too far from the robot's wrist, it creates a larger moment, or rotational force, on the robot joints. This increased moment can quickly exceed the robot's capabilities, even if the total weight is below the nominal payload. Furthermore, the moment of inertia comes into play, especially during rapid movements. Moment of inertia describes an object's resistance to changes in its rotational motion. A payload with a high moment of inertia, even if light, can put immense strain on the robot's motors and gears during acceleration and deceleration, leading to reduced performance or even failure. Therefore, payload capacity must be seen as a three-dimensional envelope of mass, its distribution, and the dynamics of its movement. So, how do you practically interpret these sheets? First, always look beyond just the single payload number. Identify the specified maximum payload, and then crucially, find the corresponding allowable moment or wrist capacity specifications. These figures tell you the maximum permissible moment of inertia and the acceptable offset for the center of gravity relative to the robot's wrist flange. For any attachment, such as grippers, tools, or even cables, remember to subtract their weight and their contribution to the moment of inertia from the robot's total capacity. Consider the operational speed and acceleration you intend to use. Higher speeds and accelerations will amplify the dynamic forces and reduce the effective usable payload. If the datasheet provides a payload versus reach chart, study it carefully, as the maximum payload can decrease significantly as the robot extends further from its base. To truly leverage your robot's potential, consider the concept of payload distribution. This means not just the total weight, but how that weight is spread out. A tall, narrow payload might exert less moment than a short, wide one of the same mass, especially when rotating. Some advanced data sheets might even include details on dynamic payload factors, which quantify how much the nominal payload must be derated based on factors like cycle time, trajectory complexity, and specific joint utilization. Understanding these granular details allows you to fine-tune your application, potentially using a smaller, more cost-effective robot for a task, or extending the life of an existing one by optimizing its motion profiles. It is about working smarter, not just harder, with your robotic assets. By taking the time to thoroughly interpret robot payload data sheets, considering not just the weight but also the center of gravity, moment of inertia, and dynamic conditions, you are making an informed engineering decision. This diligence ensures that your robot operates within its design limits, leading to predictable performance, reduced maintenance, and a significantly extended service life. It transforms a simple specification into a powerful tool for optimizing your automated processes and safeguarding your robotic investments.
If you love robotics, Like, subscribe, and keep building with us.